and go to the presentation view. Okay. Welcome everybody. As this is loading, welcome to OBI, Open Building Institute webinar number 9 on the applications of 3D printing to construction, and in particular the construction of the Seed Eco Home, as there's a lot of unique applications that we do use 3D printing for. So Open Building Institute is a crowdsourced effort, open source effort to make affordable ecological housing widely accessible, building upon the work of OSE, the machine building work, up to applying the machines to build housing. This is our build from 2016, a proud result where we built a 1,400 square foot structure in 5 days with 50 people, and then another 5 days for the greenhouse with 50 more people. This is the floor plan in general, what we have right now. And I put this microfactory in here up to the north, which doesn't exist yet. That's not built. We do have the utility room, the main structure, and the aquaponics. But the microfactory is in addition, where if we talk about 3D printing, hey, why don't we set up a little 3D printing cluster right in our home such that we can combine the productivity, the natural ecosystems, and small-scale manufacturing all in one. So what's a 3D printer? Let's get into this, and why is it so important? It's a device that typically the way 3D printers are known today is devices that they typically work on plastic. They melt plastic from a spool that's right here through a heated extruder head to make any kind of complex geometry that you like, typically on a heated build platform, so that things stick. Now this is the 3D printer in construction. I mean, the 3D printer applies to so many different things. The same kind of technology, basically a robotic XYZ axis with a tool head, computer controlled, where you can feed it any kind of program, and you can design a structure to do anything. Like, for example, house printing. A big 3D printer, like here you see with a nozzle laying out these wall patterns here, by a Chinese company. Look at that. We thought we were great with the Seed Eco Home build in 5 days. Well, these guys build 10 houses in a single day. So the promise there is, of course, the speed, because you've got the automation. One of the things I've heard about this is that if you're working with cement, so instead of melting plastic, you're just extruding cement through the tool head, layout patterns like this. What I see there, I think, is mesh, I guess, to keep this from cracking. That looks like metal mesh in there. But house 3D printing is, it's happened. How relevant is it? Well, you can print out of mud. That's kind of more our style, like we do compressed earth block. But this is a huge 3D printer. Look at this for size, for the scale there. I mean, this thing is like, what is it, like 20 meters or so tall? Little people down below, and it's a delta configuration printer with those 3 long arms that move into any kind of geometry. Here they're building this hut out of mud. But 3D printers can print also all types of other materials. Like there's initial experiments on the open source 3D printing in metal by our friends from Michigan Tech University. You can do things like print 3D print cordless drill bodies, or just about anything, any small or medium scale structure. It's all doable, and the advantage being that you can print out as complex a geometry as you can imagine. So that's good. Now, cordless drills, I mean, the promise, one of the promises that we like in terms of 3D printing is some of the environmental aspects, because if you can take the plastic, you can remelt it. We're talking about thermoplastics, things that could be once used up, or you don't throw this drill away. You grind it down into the plastic, you make filament again, and you re-extrude again for a complete closed loop on the chain of plastics. Instead of plastics all going into the waste stream and polluting the earth, you can reuse them forever. So the cool thing about 3D printing is that it's a very mature open source technology. The RepRap 3D printer project, the open source project, it's changed the world with open source replication, in that currently there's hundreds of thousands of 3D printers, and I mean that, hundreds of thousands that are built on the designs that were initially done. Like here, I think this was back in 2006, I believe, where this initial version of the 3D printer, the Darwin, made parts, all those plastic parts that went into its child. So parent-child here. Now we're not talking about printing the metal and other parts, but you can also do that. You can make, for example, an all-plastic 3D printer if you like, but it's more effective with metal, of course, to use both plastic and metal. But the idea is that RepRap stands for Replicating Rapid Prototyper. So RepRap, very nice idea, and literally the entire home scale consumer 3D printer industry has been started by the RepRap project, including the 3 other largest companies in the world that do that today. Ultimaker, there was also the story of MakerBot, which used to be the largest 3D printer company in the world. Which was based on this open source printer, but that then went proprietary. But a whole industry, a huge market is growing on this. The market value of 3D printing is about 500 million per year right now, and it's doubling every year right now. So it's a big deal. And for that reason, we think 3D printing is important. Back in history, I included the 3D printer as one of the critical tools because of its robust power to do a lot of different things. I'll talk more about that. But for us, the 3D printer leads to construction actually in a couple of ways. One, you can print various building materials, and I'll get into that. Or you can build more machines. How with a 3D printer? Well, we're not really talking about well, let me get to that. Let me cover the building materials right now. So as far as construction material goes, the 3D printer is part of the open source material production facility, which takes soil, limestone, hay, and trees and converts it to various usable products like lumber, compressed earth blocks, insulation, concrete, pellets, charcoal pellets, and paint, and glazing. Now the glazing comes from a 3D printer, but if we talk about the products of a 3D printer, you're going to be talking about glazing, plumbing, fencing, decking, and others, and I'll get into that. Now, how does the 3D printer cause you to make more machines that then build housing? Well, when we talk about a 3D printer, we really talk about the 3D printer construction set. So it's not just a 3D printer, but a universal CNC XYZ robot that can be equipped with various tool heads, such as a larger version of the 3D printer would be a CNC torch table, which is once again an XY gantry and a little bit of Z-motion that's equipped with a plasma torch or an acetylene torch that can be used to cut all the metal for all our equipment that is then used to build the house. So a scaled up version of a small 3D printer can be a larger heavy machine and larger. So about the 3D printer construction set, we start with a universal axis, an axis that's used in XYZ directions to create the XYZ motion. All these axes here in a simple 3D printer, that's what we're building right now, are the same. Here's our current build, that's our current frame, and the universal axis. What we're actually doing is adding magnets to the axes, so they are reconfigurable. These are super magnets, 8 pounds of force each, so you got 50 pounds from each pad of pull on the frame. So like 100 pounds of attachment just from these little magnets. So we're attaching these things magnetically to the steel frame so that you can reconfigure the axes in any way you want. So this is the detail of the magnetic mounts. So you can stick that axis onto the metal frame in any configuration you like. So you can go from a 3D printer to a much larger device like a CNC torch table, a router, or other heavier machines. Here's a little bit of a heavier router. And the nice idea here is that the magnetic mounts work for non-contact machines like the 3D printer, but for heavier duty things you can bolt things through like you see here. But the idea is that these axes, the carriage pieces, the plastic pieces, can be printed for very tiny machines like the 3D printer, which just uses essentially it's 5/16 inch, so that is 8 millimeter rods. But the same system can be used with 1-inch rods, so that will be a much stiffer frame, or supersize the plastic pieces and put 2-inch rods there. Now at that point you're talking about heavy duty CNC machines that can do up to things like CNC engine making machines. So the idea is there, and for the super heavy duty we might not use electric stepper motors, we might actually attach hydraulic motors to drive the system, and we might put metal plates on these plastic pieces to reinforce them, to use what we would call plastic metal composites that make for a super strong machine, but with 3D printed pieces. So the complex geometry is achieved by a 3D printer, and then the strength is achieved by the metal pieces in there. So now the modularity allows you to do all kinds of flexible scaling, such as a 3D printer with 9 print heads. Look at that. If we can modify these axes as we like, you can double them, triple them, you can add more in whatever configuration you like. You can play and do creative things. So the overall, the OBI roadmap for housing means that we can be producing materials, or the machines that then produce other machines that build houses. And we can be talking up to other things like rubber tracks for tractors and O-rings. I mean, think about that. There's so some rubbers are also thermoplastic. They can be melted down, and they're rubbery, they stretch, but they're thermoplastic, meaning that they can be melted down and reformed into another shape, which means that it lends rubber, thermoplastic elastomers lend themselves to 3D printing. Now imagine that. Wheels for bicycles, open source bicycles, big tracks for our heavy duty tractors. Yes, I mean, there is nothing stopping us here. So yeah. Oh no, did I forget to screen share? That's a good point here. Okay, thank you for speaking up. I might, okay, man, that's crazy here. That kind of ruins all the fun here, but let's keep going. I'm gonna just rewind to show you really quickly. That's embarrassing, people. Okay, let me go back in there, kind of show you what I was talking to myself about here. So let's present this right now, so you can see it now, right? It's loading up. Can you see it? Everyone can see? Okay, assuming that everyone can see, so just briefly going through all the pictures here that we've seen about the 3D printer, and you can actually, for the watching of the actual presentation that's recorded, the link to the presentation will be below, so people can go through this manually. But here are the pictures of the houses that are 3D printed that I was talking about. These huge 3D printers that print out of mud. Other 3D printing activities, parent and child, the first 3D printers based on the RepRap project. That's why we're including our own 3D printer in the Global Village construction set, leading to machines and to houses. So I'm going through the universal axis system and the frames that can be used to build any kinds of machines, seen visually here. So everyone will be able to look at this presentation afterwards to catch up to all this. So the roadmap for housing includes both machines and materials, and the special interest from OBI side revolves around recycling and local production. So the recycling part closes the material cycles. Plastic is a pervasive pollutant, and there's so much of it, and it's completely reusable, as I'll talk about, with simple infrastructures that actually right now are completely open source and doable. Opening up routes for local manufacturing, which is the relocalization of economies. So like, think about the plastic industry. That is huge. That can be brought down very easily to local communities, not in centralized manufacturing plants. Now, local feedstocks go so far as the synthesis of bioplastics from plants. We do have the bioplastic extruder within the construction set, so the production of open source bioplastic is waiting for us, and that'll happen in a few years. We're not there yet. That's getting into chemical processing, chemical reactions that we haven't done a lot of that so far. Right now, all we do is buy parts off the shelf, make some of them, and make machines. We're not so much at the feedstock level, though we're starting with that, with the open source materials production facility and producing things like bricks and lumber for this year's house that we aim to do. So the products that we talk about here that are interesting to OBI that come from the 3D printer are glazing, affordable high-performance aquaponic greenhouse builds. Now that's the result. I'll talk about that. Plumbing, toilets to sinks to showers, including the actual utilities themselves. The pipes too. I mean, that's all thermoplastics. Fencing, like fence posts, decking, outdoor furniture. Large growing beds that could be 3D printed in place. Rubber tires, gaskets, and seals, so that comes from the rubber thermoplastics. Various unusual and hard to source parts. I mean, sometimes in aquaponics, like I did with nut breeding experiments, I needed these very unusual fittings that were not to be found in a store, so I printed them. So the full tool chain of plastic making starts with grinding. So say you have scrap plastic, you're going to grind it from bottles. You grind them up into flakes or chunks or pellets. Then you can make filament, and then you design your parts using CAD software, and then you can do your 3D printer to 3D printing software and your 3D printer to print what you like. Now, strong case exists for making your own plastic because of the costs. I mean, plastic is junk. I mean, it's typically so you can get it for free or nearly for free. And if you go to the recycled, I mean, let's look at the costs, because plastic filament that you buy ready for the 3D printer is about $8 a pound or so. That's the lowest I've been able to find. But that's, once you start printing things that are heavy, that doesn't make sense. Like, for example, you can buy plastic lifetime lasting fence posts that never rot. You can get one of those for like $3 right now off the shelf, but if you printed it yourself, that would cost $25 if you printed it with the off-the-shelf filament that's already wound up for you on a spool. So let's go to making our own. So if you buy regrind or pellets, that goes way down. So the pellets, they call it resin or pellets or regrind, meaning regrind means that it's ground up waste plastic. You can get that in huge quantities from recyclers at $1 a pound, or you can go even further back to get the actual unground bales, which are like a ton, and that ends up costing you 1/10 of that. So about 10 cents a pound. So almost 100-fold factor of cost reduction if you start going back to the plastic source. So if you recycle your own plastic, that would be for free. So we have to consider the electricity costs. If the material stock is near free, like there's other inputs, that's your time and really the electricity that's used to run your 3D printer, which with its heaters and electronic controls. Well, it turns out, you can read in a paper that the electricity costs are about 50 cents per pound of finished 3D printed product. That's just in electricity. So that's not zero, it's considerable. And that's counted at 10 cents per kilowatt hour as the electricity cost. So clearly high value items are worthwhile to print, but what if you start actually printing products that are heavier, like lumber or decking, fence posts, which are heavy? Well, 2x4 lumber that weighs, say, 10 pounds, that's how much a 2x4 weighs, 2x4, 8 feet long, that would be $5 in electricity right there. That's probably what you get it at the store for if you were to get plastic lumber, so you would get no advantage outside of recycling and doing it yourself. So you really have to talk about how you could reduce that electricity cost. And when we say 50 cents a pound, that means these open chamber build platforms, no enclosure, where on the 3D printer itself, which means all the heat just leaks out. So you can talk about insulating your 3D printing nozzles and the entire build surface. That's why part of the reason why we're going to these nice cubic structures for our structure is that you can enclose that relatively easily by covering the sides. So you retain the heat and hopefully get the energy reduction of this down by a factor of 2 to 4, I would like to hope. And we'll see that in practice. So, but then the second question comes up, besides electricity costs, what about the time it takes you? Well, I think that's manageable. So for example, the Morstruder, which is an open source extruder from the Lowsbot company, it's an existing open source 1.2 millimeter aperture extruder. That's the size of the hole that emits the printed filament, the melted filament. It prints at 5 pounds per 24 hours. Not bad. I mean, that's the half of the weight of a 2x4 piece of lumber. So we can get around this. So speed up the rate. We can just use multiple print heads. So for example, 9 as in a former discussion that we talked about. So let me just check in here. So definitely, as far as print rates are concerned, definitely doable. Just put more print heads on your 3D printer, and then with the nine heads on this, the existing technology of a fast extruder head, you got 45 pounds in 24 hours. That's plenty. That's enough to go on. So think of a cluster of either 10 individual machines or one machine with like 10 heads. Yes, that can be done. So I kind of, this here shows it's a cheap way to show the scaling of this in tall and short versions. Like, we can stretch the 3D printer to be much taller or much wider. But the idea is that if you want to do things like fence posts or tubes, the most effective way is to go vertically up. If you print the polycarbonate multi-wall glazing, you want to kind of go with the grain of the print, which is up. The natural direction of a tube, the natural way you would want to print a tube is going up. If you lay it flat, I mean, it will kind of collapse on you. It's not a good way to print it. There will be, because there's still gravity on a 3D print, so you can't print a full bridge when there's nothing supporting a bridge, like a tube printed sideways. You can't really print that well. So you want to print vertically. So you want to go to a vertical 3D printer that's could be a small size, but it's just very tall. So think about 6 feet or 8 feet tall to do things like stakes or polycarbonate multi-wall glazing. So let's talk a little bit about the tool chains involved. So if you do go from the scrap feedstocks, then you have to shred them first. There's a nice project out there called Precious Plastic. Some of you might recognize that this is where I copied that from, but they have a good design of a filament shredder, of a plastic shredder, where you dump in your bottles and everything else, and out comes flakes of plastic that can then be put into a filament extruder, which basically is a hopper driven by a motor. The motor drives a screw. As the pieces fall down the hopper, the screw pushes them into the heated zone. The heaters and the screw provide heat, both by friction and by electricity, to melt the plastic, and then it comes out as a strand at the end. So you can print out spaghetti out of this, make things like filament or other things. Or think about if you put a die, a form that's like a ring, you can print out tubing using this kind of a device here. And then you'd go to a 3D printer after you have your filament produced. That's a representation of the 3D printer. Well, that's not what it is really in the project there. Okay, but look at this example of a 3D filament extruder, 3D printing filament extruder. This is a fully open source version. It produces about a half a pound of filament per hour. The accuracy, like it gets you like 3 mm filament plus minus 10%. I mean, the accuracy is really good. Material cost $250, driven simply by a small stepper motor. The electronics behind there are Arduinos and ramps, the electronic controllers from the RepRap project. So this is how the machine works. You send some, so you get a container full of pellets, stick it down into the extruder, and it extrudes a fiber, and this fiber is sent out here. Now this is the actual puller here, which controls how fast. So this is all electronically controlled with sensors. It's fully automated, where you pull the filament out. Depending on how fast you're pulling it, that determines the thickness of the filament. So you can regulate that very finely with some feedback, and then you end up winding that on the spool. So there's some trickery involved, but this is fully open source. You can download the plans and 3D printing files, because a lot of these parts here, all these things, the white stuff is all 3D printed here actually. So you can build this at very low cost. And just one more note here, the spooling is very important. There's fine controls that happen there. But this is great. Half a pound per hour. Not bad, like 12 pounds per day running 24/7. So that's decent, not too bad. I mean, very small, inexpensive. And this was actually developed as a challenge a few years ago. A foundation funded a challenge where there was a contest made to make the best open source filament extruder. Hugh Lyman is the 83-year-old gentleman who won that contest. So this is version 5 of his extruder. Now he's up to actually version 6. But it would be interesting to actually make this for initial test with open source ecology and OBI. So how feasible is it to print building materials even in a home scale print cluster? All you need is a room with a few 3D printers. So take a look at the Lyman filament extruder, 12 pounds extruded in 24 hours. So if you have 4 of these, so think of a little army of 4 of those tiny extruders, you can feed a 9-head 3D printer at the maximum production rates, extrusion rates I discussed before. So the filament extruders would cost you under $1,000 at under $250 a pop for 4 of them. And think about a 9-headed monster 3D printer, each head printing 5 pounds in 24 hours. That's 45 pounds of print per day. Under $1,000 for that. That's what we're estimating the material cost to be on that one, based on our experience with the 3D printing, because 3D printing is the prices of that, because it's fully open source, they're very benign. It's not too expensive. So the point is, if that 4 of those extruders now get you plastic from scrap, so we're talking about, think of actually making materials and selling them. Well, it would cost you a lot of money if you bought filament off the shelf. As I said, it wouldn't make sense for heavier objects, so you'd be limited. But right at home you can do 1,350 pounds, so over half a ton of plastic goods produced per month. So you can be talking about setting up a real, pretty much take over the recycling in your city and take all their plastic and make useful products out of that. So that could even be relevant for things like the structural plastic lumber and everything else. 1,350 pounds, that's a lot of plastic, and that's definitely more than we have in the Seed Eco Home right now. So you can produce all the plastic value. Yeah, I haven't counted exactly the amount of weight of plastic that's used in the Seed Eco Home. We should do that, and we will. But we know we have the greenhouse towers, we have a lot of the water storage containers, a lot of all the plumbing essentially is all kinds of plastics. The water panel with the filters, those are plastic casings. A lot of plastic. And then you can talk about various useful utensils, household goods. But you would have plenty of 3D printing filament capacity to be making the filament and extruding that at this rate. So this is a print cluster with 9 heads using a 1.2 millimeter open source extruder set. Great opportunity for local production here. Let's go through a little case study. So let's take a look at our prized multi-wall polycarbonate glazing. You can see the link there. So how would you do that? Well, start the tool chain from the very beginning. You can start with CAD. This is FreeCAD, so you can learn FreeCAD 101 by clicking on that link. We have a good instructional on the wiki. Draw yourself the structure of the multi-wall glazing. So this is a cross-section of the multi-wall glazing. That's what it actually looks like. There's two front and back surface with a cavity separated by these little walls. And I just drew that. Went to FreeCAD, drew that out, extruded that to a shape, and there we go. So then you put that into your open source 3D printing software. So Cura is what we use. Cura is the 3D printing software. You put that in there. That's a representation of the print bed. So we printed a 6 by 6 inch piece of that just out of PLA, which is a common bioplastic. And that was the result. So could we use that for our glazing? I'm very encouraged, actually. So this is not even polycarbonate. This is just PLA. And the initial results are quite promising. The structure itself is quite strong. Transparency could be better, but for a greenhouse you don't need transparency. Diffusion is fine, but you can also make it much smoother by polishing it using some solvents. So I don't know if people want to do that, but definitely solvents, you can smooth it out very nicely. If you talk about UV protection, if that's going to be out in the sun, you can paint it with some kind of a UV protected coating, or begin with additives to your resin that are UV stabilizers like titanium or carbon. Carbon would char, or carbon would darken it, so you don't want to go with dark, but maybe titanium, which has large molecules that block the light, block the UV, but also let some of the light through. So there's a whole, that could be a whole science of how do you UV stabilize that if you're using it as a greenhouse glazing. I mean, they do have, for example, marine UV stabilizers for sails, for wind sails, that could be used. So that's some trickery there to find out about. But let's look at the costs here. The 4x8 sheet of polycarbonate, 6 millimeter thick, is $45. So that's 4x8 feet, $45. It weighs about 5 pounds or so. So if you were to 3D print that yourself, you would pay $5 in polycarbonate regrind that you get from a recycling supply, and then you would pay $2.50 for the electricity involved in printing. So if you add up those costs, that would be 6 times lower if you 3D printed that at home using commercially bought polycarbonate regrind. So polycarbonate is a thermoplastic. It melts under high temperature and you can extrude it over and over again. So polycarbonate is very strong, quite durable. Now CDs, so CDs like in the CD players are made of polycarbonate too. So if you save a bunch of CDs or have all your friends bring you all these old CDs, you can regrind them yourself and then have the material for free. So that's one resource that you can recycle yourself. But if you had the feedstock for free, then you're talking 18 times lower cost compared to what you could get at the store. So in principle, we can make 9 of these panels in 24 hours. Each print head I mentioned prints out 5 pounds per 24-hour period. Each one of these panels, 4x8 feet big, weighs about 5 pounds, so about a panel per day per head. So use your 9-head printer. It only will take you a few days or a week or so to print out all the glazing for the 800 square foot aquaponic greenhouse like we built in 2015 or 2016. So there are many other things that are relevant for cost savings and production. Like here it has a picture. That's Larry Atty, the guy who actually open sourced these towers, the same towers that we're using. He's the guy that developed that design basically by taking a piece of PVC tubing or polyethylene tubing and ripping out little holes for the plants. Well, you can 3D print that structure yourself. So here's what he's doing here is using basically like these 4 or 6 inch, I think these are 4-inch tall little sections. You print out each one of them individually. You see there's one printed right there. He's got a bunch of them 3D printed. But you can print out your entire tower just made out of little pieces. So you can click on this link to see how he does that, how he connects them. So if you talk about savings on all the different materials that we use in a Seed Eco home, there's a lot of different stuff. Like greenhouse glazing, is the polycarbonate for our greenhouse cost about $2,000. We could print that at 1/16 the cost. So 150 bucks. That's 1/10. 200 bucks would be 1/10. So under 200 bucks we could print it if we paid for that electricity. And then you can talk about, well, if we get enough solar panels and they're paid for, then we could be doing solar printing, so we're not using any precious energy off the grid. So you can go think about solar 3D printing as well. Greenhouse towers, they're about $200 for the plastic for about 40 towers, something like that, about that much. They're about like, I believe like $5 a tower, or $5 or $7 a tower, times 40 towers, so there's a few $100s there. A lot of aquaponics fittings we could 3D print. Worm towers, like for growing red worms or composting worms. First flush diverter that we bought for rainwater catchment, that cost us 30 bucks just for a little piece of fitting. Separating toilet, we could 3D print that whole thing, $600. That would cost you if you bought it off the shelf. Filter housings, we paid about 100 bucks for about 6 of them. Plumbing, there's at least $200 worth of plumbing pipes and fittings. Poly water pipes, at least $100. And then think about, what about structural plastic lumber? Man, imagine we built all the wall panels out of 3D printed plastic lumber. That would be insane. But we can try that. I mean, it's going to get down. Like, once you're making so much printing, think about the capacity which I mentioned, about 1,300 pounds per month. That gets into really a materials handling operation. You have to grind it, then extrude the filament. You can automate a lot of it, but when you say receive that bale from the recycler, you're probably talking about a tractor putting it into a large grinder. If you want to make this really efficient, so have a nice large grinder, just dump the bale in there, kind of like the hopper on our brick press, which is a large hopper that can fit like a cubic, half a cubic meter of soil in our big hopper. But some operation like that where you're using big machines to move these bales, because it's going to get heavy if you're actually going to do that in some kind of a serious operation. Of course, you can do that manually as well. To move 1,300 pounds, that's easily done in a single day. But you could definitely use the help of machines if you're getting serious about this, and say going to local recycling centers and picking up from them, or having bales delivered to you. That's where the heavier equipment does come in if you're going to get serious about this. But structural plastic lumber, decking, fence posts. I just recently looked at what it would cost us to put up a fence around all of Factory Farm, which is 30 acres. And the cost is about $10,000, about $5,000 in fencing, metal fencing, and about $5,000 in fence posts. So imagine we printed them. That would be awesome. More house windows. Imagine we got the polycarbonate prints, got them really smooth, then maybe single layer or just flat layers that we shine, polish the inside and outside. We could possibly print our house windows. Now, windows are very expensive in a house. We paid at least $1,000, probably like $2,000 for windows and doors in a Seed Eco home. Then you can talk about some clothing items like shoes and belts made of rubber or rubber-like materials, and rubber tires and rubber transmission belts for the heavier equipment. 3D printed cordless drills. Like when we do our extreme manufacturing workshops, we have like 20 to 40 cordless drills on the site, we go through a lot of drills. So if we could make our open source cordless drills, that I think is actually a big potential savings, because cordless drills last between like a year to a few years, even the professional ones. So here you can be talking about recycling all the parts of a cordless drill forever. So big savings there. So that's pretty much all I have on the presentation on the applications of 3D printing. Covers a lot of what we want to do here. And currently, I'll talk about what we're doing right now and make a pitch for the OSE developers group. But our roadmap for this year, just to tell you how the 3D printing fits in there. Right now, we're actively developing the 3D printer. If you follow the OSE workshops page or the OSE Facebook, you'll see some updates on that. We're doing our first workshop in Hamburg, Germany, on April 22nd. Well, the idea for 2016 is we start with the 3D printer. Then we build the larger CNC torch table based on a design pattern that I talked about before. And then we build some more of the heavy machines, like another version of the tractor, excavator, brick press, and sawmill, and other machines. And then we build the house towards the end of the year. So there's a whole progression. But if you'd like to get involved in this more deeply, the requirement is to spend 10 hours of volunteer time with us per week. We have an interview process, and we have a dedicated working team that meets on Mondays. So if you'd like to join that and become more involved in this development, we encourage you to do so. And our goal is to release a product. So I'm gonna quit the screen share here. Our goal is to release a product of some sort, like the 3D printer, after the first quarter. Let's see. In the first quarter. So that's the first project of the year. Then following up with more of the products, and it really depends on how much of a team we build up as far as the velocity with which we can go, because we're serious about the 3D printer as far as taking that to a place where people can replicate the workshops that we do in various countries around the world. Our goals for the 3D printer are actually quite ambitious in that we are looking to do a workshop, a big grand finale 3D printer workshop in December, where we build 100, that is it, 100 3D printers in a single day using our modular construction set. And we're really paying a lot of attention to absolute plug and play modularity, simple design, like the simple frames, the magnetically attached axes, and the universal axis that's same throughout, so radically reduced parts count and everything else. So if you'd like to get involved in that, we welcome you to do so. And you can look at the OSE developers wiki page to sign up for that. Otherwise, I think I'm going to end here and take some questions if anyone's got any questions. So, yeah. Any questions? So, Donald is asking about the factory farm workshop schedule. Don't have any formal announcements yet outside of what I will send you in a chat box here. We do have a page on the wiki called Critical Path, which shows what exactly we're doing right now. But if you take a look at that link, which I sent in the chat box there, you can see that we've got the 3D printer workshop on April 22nd. And after that, the idea is that we will be running one of those workshops. That's in Germany first, but in the United States, our goal is starting in June to run one every single month from that time. And then add in, of course, there's going to be the big house build. And we might do we're very likely to do a tractor build and definitely a brick press build. We don't know if we're going to open up the CNC torch table workshop or if we're going to just do that privately here. Depends how far we are on that design. But definitely it's very important for us to develop the CNC torch table such that we can make all the heavier machines work out, built much more quickly than before. So, question, why actively developing a 3D printer if there are so many open source 3D printers? What's the difference? Good question. The answer is very clear. For example, if you wanted to do 3D printing of polycarbonate multi-wall glazing where you need the 4x8 size, there's not a single, we don't know of an open source printer that's got that worked out. So we're focusing, there's several aspects of that. One is that there's nobody in the world right now is offering a single day 3D printer build workshops. Our design is designed to be absolute minimum parts count, which means that you can build it authentically from scratch in a single day. That's a big deal. The other part about it is it's the construction set approach. So we're not just building a 3D printer. As I mentioned, we're using that same design pattern to build much larger machines, production machines, like the torch table or the heavy-duty CNC machine. So if we used an existing 3D printer, those are not designed to be scalable in any way. The other aspect of our 3D printer is we're going to use a universal controller which can handle much larger stepper motors. So the controller that we're going to do is going to be, once again, like a construction set of a controller. Our electronics are going to be, I mean, just every single aspect in terms of the production engineering, design it for the swarm build such that many of them can be built in a single large event. Why is that important? Because if you can show that you can produce, for example, the crazy idea of 100 printers in a day, that's exciting. And that now, if you can replicate that worldwide because the plans are open source, then you're rivaling factory production in terms of the volume output that you have in production ability. So that's big. So no one has the features of primarily the scalability and modularity that you not only make a 3D printer, but essentially just basically a platform for making all the different CNC machines in the world, from laser cutters to torch tables to routers and everything else. So we had to do our own because nobody is thinking along the route of modular scalable. And that's the simple answer. Like doing 9 heads on a 3D printer. The other part of that, so going further on that issue is, because we would like to see people take on the distributed enterprise, the workshop model, as a way that they make money. And for that, you need a printer that can be built in a single day. So right now, no printer like that exists, unless you want to buy somebody else's 3D printer. Take the best contender. I would say the Prusa original. That's a printer that's got 80,000 at least copies the last time I checked. So that's the best one in the world and best print quality. But it's not scalable. I don't think we can build it in a single day. It doesn't have the magnetic reconfigurable axes. It's not designed to scale. So there's the economic relevance of the workshop model, but also we're designing the whole infrastructure to have the plastic melting into the filament and producing of larger things using your print cluster. So we also want to open source the print cluster. Yeah, but as far as just the answer of why not use an existing one, well, there is no modular scalable one that's out there that meets our needs. Yep. Yeah, so that makes sense to Daniel. I'm glad I answered that. Do the panels that come from the 3D printing come with the same stability? Well, that depends how we do them and what resins we would do. So on a polycarbonate panels, we know that one side of them has got the UV protected coating and the other doesn't. So you have to, the commercially purchased product, you have to put it on a certain way. So they UV stabilize it on one side only. But whether it's stable or not depends what kind of UV stabilizer. I'm assuming you're talking about ultraviolet radiation from the sun that makes things decompose over time. If that's so, then you would need to put in UV stabilizers into the resin, or afterwards paint the surface with some kind of a UV stabilizer. So this is all the chemistry that we have to work out. I mean, this is all to be experimented with and determined. And that's why we're asking you to join the development team, because the quicker we do that, the more projects we can get done. Like, I'd love to get to the 3D printed cordless drill. In fact, I'm thinking about a Hero X challenge. If you Google up Hero X, it's a crowdfunded, crowdsourced design platform. We're considering that for the cordless drill. But yeah, difference between an off-the-shelf one, 3D printed one, and a commercial panel. The commercial panels are extruded, meaning they're completely solid. They're not going to break on you. In a 3D printed route, you do have to watch out for layer-to-layer adhesion. The weakness in 3D printing is if you have very thin material that you're printing with, the layers might delaminate because it's a big strand that you're depositing, and that sticks to itself because it's melted. So yeah, I mean, we'll see what we can do. I mean, I can theorize what's going to happen. I mean, our goal would be to get something that's actually workable, that works and can be used and lasts at least 5-10 years. I mean, you got to make it last like 10 years at least, otherwise it's you're replacing them all the time. The commercial lifetime is, I think they say something like 20 years, but that would be the goal. The goal would be to meet or exceed industry standards. So I hope that answers the question. Any other questions? Yeah. Yeah, I heard you say something about Windows. Not sure 3D printed. So, as you saw in twin wall polycarbonate, you saw how it wasn't particularly translucent. Well, you kind of want to look out your window and see what's outside, so you do want to get your 3D print to be very shiny, very transparent. Now there are ways to do that. You can buff the surface afterwards. There's techniques for getting it smooth by either applying a solvent that kind of melts the surface and makes it very, very smooth and transparent, or you possibly can paint it with another layer of something that makes the little imperfections kind of hide, and therefore the final window would look very, very transparent. So those techniques are out there, but the main thing is, if you're 3D printing, typically what you get out of the 3D printer is not exactly transparent. It's not like glass which has been melted, or like a piece of polycarbonate that's just a solid sheet that's been melted and poured. Because you've got the layers of 3D print stuck one upon another, that interferes with how the light transmits through that, which is great for greenhouses where diffused light is a plus. But in a home, the window idea would be good for privacy windows if you don't want to see outside. But if you want to make transparent windows, you'll have to post-process them after you 3D print them. So doable, would require more work, but definitely worth trying, because a window costs you like $100. Windows are expensive. That's a big cost of a house. So if you're trying to build low cost, you typically want to get recycled, reused windows. Yeah. Donald says, weekend design workshops if others are interested in as well. Yeah. For people who are close by. We are considering, definitely, as far as visitors days, like once we get the aquaponic greenhouse, Seed Eco Home finished up, we're looking at tours starting around May. We're considering some shorter crash course workshops. So we don't have this final schedule yet, so kind of stay tuned. Sign up to our Facebook or our newsletter, or the OSC Workshops Facebook page. Those are the base. The workshops page and the Facebook page are the most frequent posted places. So, yeah. Any other questions? Going? Okay. Well, I think that will wrap up for here. Thank you for listening. We're going to publish this for all the people who are not listening to this online, and then this will be made available to the more general public after our Kickstarter period is over. So thank you again for listening. Next week we will talk about something. OBI webinars, stay tuned for next week. You can look at the schedule of webinars, 3 more coming up. Next week is the automation webinar, where I will cover the design of all the automation. We don't have that installed yet, so once again we will break it down as this is the design part, and after it's all built we're going to do the actual results part. But stay tuned. Thank you for listening and have a good day. Thank you very much.